T-minus 10, 9, 8, 7, 6, 5, 3, 2, 1, 0, and liftoff of Space Shuttle Atlantis on a mission to build, resupply, and to do research on the International Space Station.
Houston now controlling. Atlantis begins its penultimate journey to shore up the International Space Station. Atlantis now on the proper alignment for its 8.5-minute ride to orbit. 4.5 million pounds of hardware and humans taking aim on the International Outpost. 30 seconds into the flight. Atlantis almost 2 miles in altitude, almost 6 miles downrange from the Kennedy Space Center already, traveling 500 miles an hour. The 3 liquid fuel main engines now throttling back to 72% of rated performance, going into the bucket, reducing the stress on the shuttle as it breaks through the sound barrier.
Welcome back, dear students. Today we are going to start one of the most interesting chapters in physics, and that is gravitation. Right? Especially we are going to learn about satellites, how they are launched, right? How they are put in orbits, what should be their speed, time period, so many other things we are going to discuss. And what is the use of satellites, right? So satellites have several uses. We use them for communication, satellite phones, for spying on enemy countries, for weather forecasting, for scientific research, right? So there are lots of applications which come out from the knowledge that we are going to get in this particular chapter. All right, so how did it all start? Right, the early observations about the planet and the solar system and our sun and all these details were actually observed by an Indian scientist, Aryabhatta, 1,000 years after him, right? The scientist called Brahe, and then there is the famous Kepler, whose laws we are going to study, right? And also Galileo. All of these scientists have contributed to several observations they have recorded, and all of these observations ultimately, finally, right, the law that the entire chapter is based on was given by Sir Isaac Newton, right? He was the one who came up with the famous Newton's law of gravitation. This is the tree, the apple tree. It's actually one of the descendants of the tree. So what that means is the tree under which apple sat. So they took some seeds from that apple, right? Because that tree cannot survive so long. So, and those seeds were planted in another place, right? And so this tree that you can see right now is the descendant of the tree under which the apple fell, right, on Newton's head. And that's the famous story. So what exactly is Newton's law of gravitation? I'm sure all of you must have studied this in school. So let's just quickly revise, right? What is Newton's law of gravitation? So he's saying that every particle of matter in the universe, so please note the word universe, okay? So this law is a universal law, right? It's applicable throughout the universe. It's not simply for our planet or our solar system. All right. So what's ahead? So every particle of matter in the universe attracts. So Newton's law of gravitation mentions that the force is always of attraction. That means when the apple fell from the tree, right, the moment it got detached from the tree, it did not start flying upwards. It was not repelled by Earth, right? Gravitational force is always of attraction. All right. So what about the force? So every particle attracts every other particle with a force which is directly proportional, okay? Directly proportional to the product of those two particles who are attracting each other, right? Product of their masses. So I can say F is directly proportional to, so since it's directly proportional, I'm going to write it in the numerator, M1 into M2. Why is that? Because we have to consider the product of their masses, and also inversely proportional to. So when I say inversely proportional to, it's going to go in the denominator, right? What? The square of the distance between their centers. So if I call, the distance between them as say R, right? Generally in physics distance we use the letter x or s, And in laws like this, we also use very commonly the letter R. So R square, right? So this is called as the famous inverse square law in physics. So this law that force is inversely proportional, right? So it's going to come in the denominator. Force is inversely proportional to square of the distance. This is applicable not just to Newton's law, it is also applicable to several other laws in physics, which we will discuss eventually, right? So right now this is the law. F is proportional to product of masses and inversely proportional to the square of the distance. Alright, so what we generally do is we replace the proportional sign with an equal to sign. So if I replace the proportional sign with an equal to sign, I have to put a constant. So what is the constant? The constant here is called as G, capital G. Okay, so m1 m2 by r square, we can just write it again. And what is this G called as? It is called as the universal gravitational constant. Please note, it is a constant which is universal. So again, this constant is, right, the value of it is fixed throughout the universe. It's not just for our planet. Okay, so what is the value of this constant G, right? So what do you think? Can you guess? So I'm sure some of you might be thinking it is 9.8 meters per second square. This number you have heard somewhere in school, right? So is this the value of G? The answer is yes, it is the value of G, but not for capital G. It is for something else, right? It is for the letter small g. So what exactly is this number, right? What is capital G then? It is 6.673 into 10 raised to minus 11. Alright, and let's check the units here. Newton meter square per kg square. So why are the units like this? So if you want the unit for G, can I take this r square? I can say G is equal to, take this r square in the numerator. So I'll get force into distance square, and these two terms m1 and m2, the product, it will come in the denominator. So I'll get G is equal to Fr square divided by m1 and 2. So F is Newton, r square is meter square, divided by m1 into m2 is kg into kg, so it will become kg square. So fine, that's the unit, that's the SI unit. See the number 6.673 into 10 raised to minus 11. What does this number tell us? It's a very important number to understand. So if I want to find out, let's say, the gravitational force between an object, let's say for example you, the gravitational force between you are sitting and watching this video right now. So if you are sitting in a room, there must be objects around you, right? There must be a door, there must be walls, a table, a chair, or whatever. There are things around you. They also have a mass, you also have a mass. Let's simplify the numbers. Let's say the distance between you and some object, some heavy table, let's say, is 1 meter. So let's make the denominator 1, so 1 square is 1. So my question to you is, are you experiencing, according to Newton's law of gravitation, are you experiencing, are you feeling it? Are you feeling any force between you and the table? Is there any force of attraction? Are you getting attracted to the table? Or are you getting attracted to the wall? Right? Or are you getting attracted to anybody or anything else? Right? If it's any person, it may be due to some other reasons, but not because of gravitational force. Right? So why are you not experiencing? Why are you not feeling it? The reason is this number. Right? Your mass may be say 50 kg and the table is another 20 kg. So 15 to 20, that's fine, divided by 1. But look at the value of this G, especially the power. 10 raised to minus 11, it's practically 0. 10 raised to minus 11 is 0.000, there are 10, 11 zeros, right? So multiply that by whatever is going to give me approximately equal to 0. That is the reason you don't experience any attractive force because of gravitation. Okay, you can experience attractive forces, but I'm saying gravitational attractive force due to other masses around you, right? So what is the only mass that is attracting you, which you are actually feeling? And that's the weight of your own body, because the earth is pulling you. The pull of the earth, right, was the name of the chapter. Pull of the earth is pulling you down. Why? Because your mass may be 50 kg or whatever, But the second mass here is Earth, and Earth's mass is very, very large. It is of the order of 10 raised to 24 kgs. So that 10 raised to 24 can tackle off this 10 raised to minus 11. The 10 raised to minus 11 that you see here, right, that number can be still made significant enough because of the presence of 10 raised to 24 kilos of mass. So unless you are on some extremely heavy object, like for example a planet or any kind of heavenly body, right, you are not going to experience this gravitational force. But according to the formula, that's how it is. Okay, so what about that number 9.8? What exactly is 9.8? Because this number also you have heard, and there is no 10 raised to minus anything here. It's just 9.8 meters per second square. So what is this number? Okay, so let's understand that. So I'll ask you one question. What is your weight? Right? So we'll not ask these questions, this kind of question to a girl, right? At least the boys can think about it. What's your weight? Right? So some of you may say, okay, it's 50 kg. Somebody little bit heavier may say 60 kg. Okay. So is this correct? Let's understand, where is this idea of measuring weight in kilos coming from? Because you see, in everyday life also, right, we use these numbers 50 kg, 60 kg, but this is wrong. Okay, why is it wrong? So you see, this concept is coming from, it's carried forward even in objects. Like for example, if you go and buy some product, right, some consumer product you go and buy from the mall or a shop, right, grocery shop, say you buy a bag of rice. So this photograph I've taken is of the back of a bag of rice, which is of 5 kilos, right? So please note, what have they written? Net weight. That's what we are talking about. That's what the question, right? That's the same question I asked you. What's your weight? So they are also writing the net weight is 5 kg. All right. So this, please understand, is wrong, technically speaking. For daily life, common man language, you can use it. But the moment you start attending a lecture in physics, please note, you have to be more precise about the terms that you are going to use. Why? Okay. So I'll give you an example. Suppose I ask you, what's the time? Okay. So if I ask you what's the time, and if I get the answer that it is 10.3 or 1030 feet, you would obviously start wondering there's something wrong. Or if you ask me, what is my height? And if I say instead of 5 feet or 6 feet, if I say 5 a.m., right? Are you getting the point? Time cannot be in feet. Height cannot be, the units cannot be chosen as am. Time can be in am, height can be in feet. Okay, or distance can be in feet or inches. Similarly, if I ask you, what is your weight? Right? And if you are going to answer in kg, it's wrong. It's a wrong unit. Okay? They are proportional. Okay? If you know the mass, what is this kg? It is actually the unit for mass. If you know the mass, then the weight is proportional to it. Heavier the body, more is its weight. More massive the body, more is its weight. But it's not equal. I'll give you another example in physics. If I ask you how hot or cold is the room that you are sitting in right now, then what would you do? If your AC is on, you will just look at the AC and see the temperature. Okay, if you have set it at say 24 degrees, right? Then you will say, okay, the room, how hot is the room or how cold is the room? You will say 24 degrees. But if you think about it, I asked you heat, right? How hot or cold? I'm asking you information about heat. And heat is a form of energy which should be answered in joules or calories. Whereas what are you answering me? You are giving me a temperature which is a different quantity. You understand? So the same thing is happening here. We need to understand weight is not mass. Weight is a force, right? And what is the unit for force? Let's see the formula. Basic formula everybody knows. F is ma, right? It's a very common formula you must have seen in school. F equal to ma. So force is mass into acceleration. So when this force is because of a planet or because of an extremely heavy body, then that force, or for us it is because of Earth, right? So because we are on Earth. So when this force is because of Earth, we call it as weight, W. The mass M remains the same, right? Mass is mass, there is no change in it. Mass is measured in kg. So when this force, right, is because of Earth planet, right, and we call it as weight, right, and this weight or the force is because of gravity, then this acceleration, we rename it as acceleration. We still call it as acceleration, but now we add the words due to gravity. So this small g is actually acceleration due to gravity, and it is clearly different from capital G. Capital G was universal gravitational constant. Please, these names are fixed. Okay, it's not some random name. You need to know these names. Capital G is universal gravitational constant. Small g is totally different. It is acceleration due to gravity, right? And that's why, check out the units again. It's meters per second square. Okay, 9.8 meters per second square, right? And please note, the unit for force is going to be in Newton. Okay, so if I talk about the weight again, which was 5 kg, right? And now if I really want to, this information we know it's not weight, it's net mass. So if I really want to find out the weight as per physics, okay, then I should do the mass here is 5 into 9.8, which will give me the number 49, and now the units should be newtons. Okay, but please don't answer the unit or the number in Newton if somebody else asks you this question. If a physics student or a physics teacher asks you what is your weight or what is the weight of a body, then yes, if you answer in Newton, it is technically correct. But in daily life, we still go by this language. Okay, we will still measure the weight, right? We will just refer to it as the mass. Why is that? Because anyways, this number 9.8 is supposed to be a constant, right? 9.8 is a constant. So whatever be your mass, if I'm just always going to multiply by 9.8, so I might as well tell just the mass as the weight. Okay, that is the reason why often mass and weight are considered to be the same, although technically they are different. Right? So now what we are going to do next is this number 9.8, I said, is a constant, but still going into more details. Now we are going to study that this small g has some variations. This small g, technically speaking, is not a constant. Okay, small g changes due to height, it changes due to depth. Okay, if you go above the surface of Earth or if you go below the surface of Earth, right, it will change. It will change because of the rotation of Earth. The Earth is spinning, right? The Earth is a globe which is spinning. So because of that rotation, small g is changing slightly. And also the value of small g is changing because of the shape of the Earth. So today's lecture we are going to discuss these 4 variations. Okay, but before we go into the details of these variations, your obvious question should be, why are we studying g? Isn't it just enough to know that it's 9.8 and maybe it may be varying a little bit, but fine, it's 9.8. I need to anyways know the mass. Okay, so why is the study of small g important to us? Okay, obviously for satellites which are at a very large height, right? Satellites are at a very great height. They are above the surface of Earth. They are in space, out of the Earth's atmosphere, right? So obviously, if they are going to be there, we need to know what is the value of small g there. It has to be considered while designing the entire rocket and the satellite. Okay, small g, it's not just about in space. Okay, it's also about here on Earth for designing dams. Okay, because based on the location, the dam, you see the dam is holding all the water coming from the river, right? It's blocking the flow, and slowly the water is being released, and then you can have the turbines, and the water moves the turbine and you can generate electricity, right? So this dam has to withstand the entire weight and the force, right, of the water. And how much is the force that the water is going to exert on the dam will depend on the value of small g at that location where the dam is constructed. Okay. While constructing tall skyscraper buildings, again, their height, they are not very close to the surface of earth. Smaller buildings are fine, but very tall buildings, they are quite high up in the sky. So again, how much is the gravitational force or the change in the gravitational force because of the change in g, small g, right? We need to consider that while designing the building, right? Accordingly, the material, the cement, right, that is used in construction of the building, especially at the larger heights, right? These terms have to be controlled based on the value of small g. Okay. Then we also discussed that small g is going to change with depth. So how is that useful? So you can see here, underground tunnels, right, are made, especially, you know, if you want to go under the ocean, right, or maybe through a mountain, right? So when these tunnels are made, again, the value of small g, especially if it is under the surface of earth, right, at a depth. So the value of small g at a depth has to be considered. All right. So another, right, reason why the value of small g, the variation of small g, has to be studied is a very interesting concept here called as gravity map of earth. Okay. So what is a gravity map of earth? So you can see here the whole globe here, right? Earth, well, earth is a sphere, right? So what is this weird shape here? This is called as a geoid. Okay. So what is this geoid? Geoid, here you can see the earth is not exactly a sphere, but the surface of earth, if you remove the ocean, I mean if you remove the water from the ocean, then you will notice the actual surface of earth, right? If you go into the ocean, it's all water, but below the water there is ground, right? The water is on ground. So that ground level is varying. It's not a perfect sphere. If you add the water to it and look outside from space, yeah, it appears to be a sphere. Okay, but actually, you know, the shape is like this if you remove the water. So as you saw the different continents, okay, if you see the different continents, right, like here, right here is India. Okay, this is the Middle East, and these are the Far East continents, and that's, you know, going further you will get Africa, and then behind will be the North and the South America, right? So this here shows you the variation, the level of variation in small g, and this, the color, if it is red, it means it's a higher value of small g, and if the color is blue, it's a lower value of small g. Okay, so if you see again the continents, right, so that's the US, okay, South America, and this is Australia here, the Far East, that's India coming up, it's the Middle East, right, Europe. So the small g value, if you notice, right, it's not the same everywhere because of the geoid shape of the earth, right? So the blue value gives you the smallest value of small g, and this helps us to decide the location of a launch station, right? Satellites are launched, right, using rockets. So if you have seen any rocket, right, while launching, right, you can't just take it anywhere and launch it, right? So they have to be launched from a particular location. So where to choose that location? So the preference is somewhere close to the equator, and the best place actually is India, and even India's launch station is somewhere in the south, near Trivandrum in Kerala. Okay, so again, the variation in small g is helping us decide a very important fact, and that's one of the reasons why we are going to study it. Okay, one more reason. So variation of small g, not just on earth or due to earth, right? what about the different planets, right? So we are trying to explore different planets, right? We have already sent probes to Jupiter and Mars and even Pluto, right? As far as Pluto. So if one day from now, maybe, a few decades, a few centuries, I don't know, but if ever mankind reaches on another planet, then we need to know what is the value of the acceleration due to gravity on that planet. And you can see here the different planets. The green one is Earth, 9.8. Now compared to 9.8, see the value of small g if you were on another planet. For example, we are trying to go to Mars, right? So if you go to Mars, the value of small g is 3.75, right? So if I round off 9.8 to, let's say, 10, okay, then on Mars it's a little over 1/3 the value on Earth, if you consider. That means if we go on Mars, right, our body will feel, we will feel as if our weight has reduced by 1/3, almost 1/3. That means if we try to jump on Mars, we will be able to make a very big jump. Even on Moon, actually the gravity is less, right? Mars and Moon, these are the two places that we are currently really trying to go and establish, some kind of settlement there. Whereas if we go to Jupiter, just see the value here, 26, right? If I take 9.8, round it off to 10, then this is 26. So this is 2.6 times, right? More than 2.5 times that of Earth. That means somehow if we reach Jupiter, right, and land on Jupiter, you might not be able to come out of the spacecraft. It will be a big challenge just to lift your hand. Say if you are 50 kgs mass, and let's assume your hand is, say, 5 kg, okay, out of the 50 kg, 5 kg is your hand. Then your hand will feel 2.5 times or 3 times, if I consider, will be 15, right? So 10 to 15, so somewhere in between, let's say 12 kg. You will feel as if when you lift your hand, your 5 kg hand, you will feel as if you are lifting a 12 kg body. That means if you are trying to walk, just stand up and walk, get out of the spacecraft that landed on Jupiter and walk on Jupiter, then you will feel, if you are 50 kgs, okay, 2.5 times, you will feel as if you are moving around a 120 kg body. So if we go on different planets, alright, we need to consider what is the value of small g there. That's why the study of small g is very important. Okay, so finally let's start with the formula. So how do we get the formula? That number 9.8, where did it come from? Okay, so basically we are saying the weight is because of the gravitational force, right? And what is weight? Weight we always write as, weight is a force, so mass into acceleration, and the acceleration here is g. So I can write weight is mg, and the gravitational force we already mentioned the formula, it is g m1 m2 by r square. So here if I talk about Earth, so let's say the radius of Earth is r, okay, the radius of Earth is r, m1 into m2, let's say m1 is Earth and m2 is that body whom we are talking about, right? So small m, right, whose weight we are considering. So can I say the small m is going to get cancelled off, and that's it. I get the formula for small g. It's going to be g capital M by r square, where g is the universal gravitational constant, which is 6.673 10 raised to minus 11. Capital M is the mass of Earth. To be very precise, it is taken as 6 into 10 raised to 24 kg. And r here becomes, say we consider our weight, right, weight of human body, then r becomes the distance between our body and Earth. But we are on Earth, right? So what is the distance between us and Earth? So if you consider like that, then you have to take the distance from the center of Earth to us. So if center of Earth to us, and we are on the surface of Earth, so center of us, Earth to surface of Earth would be the radius of Earth. So that radius of Earth is 6,400 kilometers. So these numbers you'll have to memorize. Okay, 6,400 kilometers, then 6 into 10 raised to 24 kg, and this 6.673 10 raised to minus 11. If you plug in all these numbers, you are going to get the number 9.8. That's where the number 9.8 comes from. Okay, so now let's talk about the variation of small g due to height. What happens if you go above the surface of Earth? What is going to happen? Alright, so small g is gm by r square, right? That's our basic formula for small g. Now, if I want to find out the value of small g at a height h, okay, then I can add a suffix here h for height h. So capital G is the universal constant, mass of Earth is not going to change, but this distance between the body and, at a height h would be usually a satellite. So the body and the satellite would be then r plus, the body and the Earth, satellite and the Earth would be r plus h, right? So instead of r square, we have r plus h the whole square. Okay, so this is one formula we get for GH. What we can do now is, this GH that we got, we can divide it by small g. Okay, so GH is this, gm by r plus h the whole square, and this divided by small g. So small g I'm going to take from here. So since I'm going to divide by g, instead of gm by r square, I'm going to write r square by gm, the inverse, right? Because I'm dividing by g. So this gm is a constant, it gets cancelled off, and I'm left with r square and r plus h square. So we can just take r, the numerator and the denominator, in a common bracket and write it as r upon r plus h the whole square. Okay, and if you take this small g in the numerator now, so you can write it as gh is equal to g into r upon r plus h the whole square. Okay, so we have three formulae here. First formula is g equal to gm by r square. Second is gh is equal to gm by r plus h the whole square. Third one is gh is equal to g into r upon r plus h the whole square. What are the three formulae for again? This first formula here, the first box, is for the value of small g on the surface of Earth. These two are the value of small g at a height. This formula, the second one, is simply based on the values about Earth, mass of Earth, radius of Earth, h, right, the height, and universal constant. Whereas this one, GH, the third formula, is based on the value of small g on the surface and simply the radius and height. We don't need the mass of Earth, we don't need the capital G value, right? It is simply, if you know the value on the surface of Earth, put that here, and if you know the height, because anyways capital R is a constant, if you know the height, you can find out GH. Okay, so these are three formulae for small g, right? And these two, the second and the third one, are for a height h. Now there are some special satellites. These satellites, you can see this satellite here, this is a satellite, and these are the solar panels, right? And what's below, what is all this? You see, that's Earth basically. That's how Earth looks like, right? From if you were standing next to the satellite, this is how you would see the Earth to be, right? So the point is, this satellite here, can I say, if I can see Earth so clearly below, right, that means this satellite is very close to the surface of Earth. Such satellites which are orbiting around Earth, very close to the surface of Earth, they are called as LEO, low Earth orbit. Their orbit around Earth is very low. So it's called as LEO, LEO, low Earth orbit satellites. Not all satellites are like this. Most of the satellites that we have launched are actually LEO satellites. Why? Because if we need them for, let's say, weather forecasting, then why keep it very far away from Earth? If we need it for communication, for satellite phones, for GPS, what is the point of keeping such satellites far away from Earth? So most of the satellites are very close to the surface of Earth. But satellites which are used for spying or for scientific research, now spy satellites, you may not want to keep them very close, because there is a chance, although according to international laws it's not yet allowed, but you can shoot down the satellites. That's what India did at the beginning of last year actually, right? In 2019, as a scientific experiment, India developed a missile which can shoot down flying satellites. Okay, and they did one experiment and actually shot down their own experimental satellite. Okay, India's own satellite. So that is a possibility. So you might want to keep it far away. And satellites which are meant for scientific research, right? Say you want to do some research about the sun, then what's the point of keeping the satellite close to the earth? Okay, so some satellites are far away, but most of them are these kind of satellites called as LEO satellites. So for these LEO satellites, okay, we have a different formula for small g. Okay, so again our three formulae are these: G, GH and GH, two formulae for GH. Now a third formula for GH, okay, this is the fourth formula on G, but the third one for GH at a height edge. This formula is only for LEO satellites, it's not for all the satellites, it's only for LEO satellites. Please note that. Okay, it is GH is equal to small g into 1 minus 2h upon r. The derivation for this formula, okay, we will derive it later on using the zip files which all of you have, the pages which I have given you. Okay, so using that during the exam, a few days before the exam, we will just quickly run through all the derivations which are required. Right now our focus is just on noting down the formula and understanding it. Okay, so 1 minus 2h by r again is only for LEO satellites. Okay, what about depth? Because for the tunnels and mines we need to know the variation of small g with depth. So again the formula is quite simple, very similar to the formula for LEO satellites. Small g, instead of 1 minus 2h by r, we now have 1 minus d by r. The number 2 is removed and the letter h, small h, is replaced by d, where d here is the depth which is measured from the surface of the earth. Okay, so g into 1 minus d by r, and again there is no concept of LEO here, this is for any depth. Okay, and what about the variation of small g due to the rotation of earth? Again we will not derive, we will just take the formula for granted. G dash we can say, right? G dash indicates the small g due to the rotation. Okay, it's g on the surface of earth minus r, that's the radius of earth. This letter here is a Greek alphabet called as omega. Okay, the capital omega. Omega square cos square phi. This is square. Okay, it's omega square cos square phi. So r omega square cos square phi. So omega is the angular velocity of earth and phi is what we call as the latitude. Okay, phi is an angle, latitude is an angle, latitude and longitude, right? They are always they are angles, they are measured in degrees. Okay, so based on the location of the body on earth and the rotation of earth, right, the value of small g is going to change. So what about the variation of small g due to the shape of the earth? So what is the shape of the earth, right? So we always say that the earth is a sphere. Okay, so but actually if you observe very closely, right, if you see these two spheres, right, earth is spinning also, but if you carefully notice the two spheres, especially notice here at the poles, you see the second one, the second earth that I have shown here is slightly flattened towards the poles, right, both the poles, north and the south pole. And if you compare the diameters also, diametrically also, the earth is slightly bulging at the equator. And why is this happening? This is happening because of the rotation of the earth, because of the spinning, right? Because of the rotation, the water especially is, getting more accumulated towards the equator, and that's why, right, the shape of the earth is, we say, flattened at the poles and bulging at the equator, and because of this shape also the value of small g is going to change slightly. Okay, so that's all for today. More details about this variation we are going to discuss in the next lecture, and also about how satellites are actually launched. Okay, so bye bye and see you in the next lecture.